Things are simple in the Southwest. It is very clearly getting drier, and it has been for the past 2 decades or so. We are very clearly at kind of the forefront of climate change here. We're going to have to make some kind of hard decisions in the not so distant future.
I grew up in the Southwest, so I was always outside, in pinyon juniper woodlands in the desert and being exposed firsthand to the impacts of drought, grazing, poor land management practices. My name is Kiona Ogle. I'm the principal investigator on the Macrosystems Legacies project.
We are really interested in this study in understanding memory and tree growth.
Evaluating the impacts of droughts on ecosystems in the Southwest, and particularly focusing on wooded ecosystems, forests, and woodlands, and trying to understand how long droughts continue to impact ecosystem functioning in plants and with respect to growth, carbon cycle. But we're also exploring the effects of extreme wet years, but in general, trying to understand the role of extreme climate events on carbon cycling processes in the Southwest.
One of the really clear examples of what's called a memory effect is something we call drought legacies.
If there is a drought last year, is that going to impact what we see in growth this year or the following year or the year after that?
This lingering effect that event has, that you continue to see its imprint on the ecosystem many years later.
Memory is kind of the idea that things that happened a few years ago or in the past at some time can impart information onto what's happening now.
The combination of environmental conditions that a tree experiences is going to have a lasting effect in how they respond to conditions multiple years from now. When I was first started to use the term memory to describe how plants and ecosystems remember past events, I got pushback at conferences or something because plants, they can't think, they don't have a brain. But I use it as an analogy to describe how certain events or conditions, environmental conditions, at some point in time will continue to impact the plants or ecosystems.
Years after drought, we see really reduced growth on average across many trees in the western U.S. And so if you think back to 2002 or 2012 or 2018, these really widespread important drought events, definitely trees grew less then. They also grew less for a couple of years after, even though conditions may have been good, wet, favorable for growth.
We're working on how do all of these climate variables interact to affect tree growth every year, especially since we know that climate is changing. So it'll be really important to predict how trees are going to respond to future climate.
Just kind of came together as people that we know we like to work with have complementary skills, and that we could span sort of the range of expertise from plant ecology, ecosystem ecology, statistics and modeling, and remote sensing data.
Cool thing about this project, a really exciting thing about this project, is that there are people like me who are really interested in using flux tower data. And then there's obviously plenty of tree ring enthusiasts on this project. I think what this allows is that we get to come together around these very interesting scientific questions, and we contribute that together to kind of learn from each other.
For this project, it is allowing us to address large-scale questions that integrate data from small scale up to a grid cell. In order to do that, to address the kind of questions we're interested in, no single person is going to have all the expertise.
As a scientist is just a gold mine to not be limited to your own perspective.
I was actually surprised. This is the first proposal we submitted to the Macrosystems Biology program, and usually you can expect to get rejected 1 time, 2 times, and maybe get funded on the 3rd time. But they funded us with the first time around, which I was, really excited about.
When they got the grant for this project, it was really great because that meant that the next 5 years I could continue working on tree rings.
So here in Arizona, we're actually in kind of the birthplace of what's called dendrochronology, and this is the study of the past with tree rings. One really neat thing about working in the western U.S. and the Southwest in particular is that there is all this data already available. People have been collecting tree cores and measuring tree rings for nearly 100 years in Arizona specifically, and so there is a really deep record of data to draw on.
Tree rings themselves are the annual increments that a tree grows each year. If it's a wet year, it's going to grow much larger. If it's a dry year, it's going to grow much less. We take what we call an increment borer, and it's like a little hollow drill bit that has a handle attached to it. And then we crank that into the tree, and we extract basically a pencil-sized thing from that shows us all of the annual rings. So this is an example of what a core looks like. When we pull this out of the tree, and you can kind of see on here, there's all of the annual rings, these dark spots, so we can see how much it grew in a given year.
And so we're using those tree ring records to understand, well, how well trees are doing with these, accelerating drought events that we're seeing in the Southwest. How trees are doing with this, record hot year that we had last year in 2023. Do we see that show up in tree ring growth records? Do we see a particularly narrow ring? And also, a big part of this project is looking at the memory of those events. For sure, we know that drought reduces tree growth, but what happens the year, 2 years, 3 years, a decade after? Some of what we know from some tree ring records shows that trees really remember those extreme drought and heat wave events for a pretty long time, and those leave a legacy or an imprint on their tree growth. And that has really big implications for, again, that global carbon cycle that many of us are so interested in. We're really focused on trying to link tree growth to atmospheric scale the carbon cycle, essentially. So we're trying to understand how variation in carbon dioxide in the atmosphere associated with sort of whole landscape scale photosynthesis and respiration, whether or not that is exactly matched or offset, or how much of that is explained by tree growth, essentially. And so the field of work that we're doing is really focused on going to these, a couple of neon sites to link our tree ring information to these long-term eddy flux covariance records.
Be working with eddy covariance flux tower data. I'll be using that data to look at the legacies of drought events, basically studying the shorter term impacts of these droughts.
What you can get from that is how much carbon dioxide is either coming into a forest or going out of it at pretty large scales. These are really useful because they allow us to scale up these things that we know are happening at the leaf or at the tree level to ecosystems and really whole landscapes.
Because the eddy covariance towers are measuring other environmental variables, can identify drought events. As part of what I do with CUNA is I try to identify flash drought events, which happen very quickly. They're like rapid dry downs of soil moisture. Once you identify these events, we can look at how the drought might impact that season's flux, which is hard to do with data that is reported on an annual scale because you can't get within the year, whereas in fluxes allow us to look at daily, weekly, monthly, hourly impacts.
If we ask people if they're interested in what's going on with climate change, they're probably not interested in how much a single tree is growing. They're interested in what's going on like in California or in the Western United States. And so the way that we get to that scale is really by using these eddy flux covariance towers.
I think eventually we want to get to the point where we are actually synthesizing all these data sets across the different scales. So right now we have individual projects with kind of small teams working on them. So there's like tree ring group, there's a flux group, there's the ecosystem modeling group and the remote sensing group. And we're sort of doing things separately, but we, talk with each other about what we're doing. Ultimately, we want to get to the point where we actually are synthesizing the data from across these different scales. So bringing tree ring data together with flux tower data, with remote sensing data, and also using that data to inform the process-based ecosystem models are being applied across the whole region. So ultimately, we want to get to that point where we can actually evaluate these legacy effects via sort of the lens of all these different data sets and the process models. We're not there yet, but we're building up the components to get to that point.
Trees are really at the heart of how carbon moves through our biosphere.
Carbon is the backbone of life. And there's carbon stored in our soils, in the rocks, in the oceans, and in the atmosphere, and in the trees. The carbon cycle, or the global carbon cycle, is how much carbon is stored in those different reservoirs, and how is it cycled through those reservoirs over time. Carbon dioxide is a major greenhouse gas. And the more carbon or carbon dioxide in the atmosphere, the warmer Earth will become. It's like when you're sitting outside on a cold night and you wrap yourself in a blanket. That blanket is trapping the radiant heat energy from your body and keeping it close to you, keeping you warm. That's what greenhouse gases do in the atmosphere. So when we have large drought events or extreme heat events or shortage in precipitation or water availability to plants, they become stressed just like we do. So if we're stressed, we're not going to function at our best. Under drought conditions, plants are not taking up and storing as much carbon over time. And if the stress of those events becomes too significant, plants can actually die. And then when they die, that carbon is lost back to the atmosphere. And so what this project is focusing on is looking at dryland ecosystems, which can be really important for that taking up and storing of carbon over time. And we really want to understand, how are these systems going to behave in the future? If we have more intense droughts, more severe wildfires, more extreme events into the future, will these ecosystems take up less and less carbon over time? And if so, that means more of the emissions that we generate as humanity are going to be retained in the atmosphere. When we think about the global carbon cycle, humans are part of it. The things that we do in our daily lives impact the carbon cycle. It seems like a pretty big thing that we as humans can do. But our activities are actually manipulating the flow of carbon. When we burn fossil fuels, we're just putting that carbon right back into the atmosphere at a much more rapid time frame that happens naturally. Oftentimes what we see is individuals feel like, I'm so small, how could I possibly influence future change in that way?
Studying these things can give us hope.
I think it's important to continue to make efforts to understand these processes as best we can, doing what I think I can in my capacity to help and serve our natural, beautiful places.
Because we are part of the Earth system, we are actually influencing the Earth system, whether we realize it or not. Things that are happening in the Arctic or happening in the tropics aren't just happening in those regions. They have actually tangible, profound impacts on our lives. You can't say that that's happening so far away, it's not going to impact me. It will. Whether you realize it or not, it will. If we don't think forward about future climate of the Earth system and how that will impact the systems that we rely on, we're doing ourselves a disservice.